about rotational dynamics. We'll start by defining torque, and then use that to define the rotational equivalent of Newton's second law. We'll learn how to use extended free body diagrams. Then we'll do a sample problem in rotational dynamics and another one in statics. Torque is a rotational equivalent of force. If you apply a force onto an object, and instead of accelerating that object in a translational manner, it rotates the object about a pivot point, what you've done is you've created a torque. Torque is R cross F, where R is the position from the pivot point to the point where the force is applied, and F is the force. You can write the magnitude of torque as Rf sine phi, where phi is the angle between R and F. You find the direction of torque using the right-hand rule. Newton's second law states that the sum of forces equals mass times acceleration. The rotational equivalent is that the sum of torque equals the moment of inertia times angular acceleration. Let's consider a plank of mass m and length L on a fulcrum. Let's place a block of mass m to the right side of the fulcrum. It would be helpful if our free body diagram not only put the forces onto the diagram, but also where they applied and the angles that they are being applied. This is an extended free body diagram. It shows the plank as a length of a bar. It also shows the normal force pushing up from the fulcrum, the gravitational force pulling downward at the center of mass of the plank, and the normal force from the block, a distance r1 from the fulcrum. We choose a pivot point in a direction of positive rotation. For this problem, we'd probably choose the pivot point at the very center where the fulcrum is, and we can choose the positive direction of rotation here as being clockwise. Now we'll write a net torque equation from our extended free body diagram, using that the torque equals Rf sine phi. We've noted that the clockwise direction is a plus for the rotation. Sum of torque equals I alpha equals the normal force on the plank from the fulcrum. That's times 0 because the distance from our pivot point is 0, times sine 90, which would be 1, plus mg, our gravitational force, but it also has a multiplication of 0 because it's at the pivot point as well. The only term that survives is the normal force on our plank from our block, times r1, which is the distance, times sine 90, which is the angle between r and f. Now let's do a problem. A block of mass m is attached to a cord wrapped around a flywheel with mass capital M and radius r. What is the acceleration of the block? We'll start by drawing a diagrams. We'll think about assumptions. We'll define known and unknown variables. Start with general equations and specify them for our system. We'll solve them symbolically in terms of given variables and analyze our result. Our assumptions here will be that there's no friction in the pulley, that there's no air resistance on the falling mass, that our string is inelastic and massless. We know the mass of the pulley, the mass of the block, and the radius of the pulley. What we want to find is the acceleration of the block A. Let's start by drawing a free body diagram of our falling block. We'll put the plus y in the downward direction to keep the acceleration positive in our equation. We have mg pointing downward, the tension force smaller pointing upward because it will be accelerating downward. Then we'll draw the free body diagram of our flywheel. It does have a normal force opposing its mg force, its gravitational force, where it attaches to that bar. Those will counteract each other, and we really won't have them in our torque equation. The only torque acting on it would be the tension in the string at the distance r. Start by doing a sum of forces for the small block. Sum of forces equals ma equals mg minus tension. Our torque equation, notice we have it plus clockwise to keep a and alpha both being positive in the same direction, in the same sense. Sum of torque equals I alpha equals the tension times r times sine 90 degrees. I can solve my first equation for tension. Tension equals mg minus ma. I also have a relationship between acceleration and angular acceleration. Acceleration equals r times alpha, and I know the moment of inertia of the pulley, or the flywheel. I equals 1/2 mr squared. I can make those three substitutions in my equation. The I goes to 1/2 mr squared, alpha goes to a over r. I substitute in for tension. I get 1/2 mr squared times a over r equals quantity mg minus ma times r. Solving that equation for a, I get that the acceleration is 2 times mg divided by a capital M plus 2m. I might want to look at a little different form for this for my analysis. If I divide through by little m, I get that the acceleration equals 2g over quantity 2 plus capital M over small m. This makes sense. The larger mass of the flywheel, the larger it is, the smaller the acceleration is. That makes sense because a more massive flywheel would slow down the acceleration of the falling block. Also, the larger little m is, the larger the acceleration, and that makes sense as well. The larger the mass of the falling block, the higher the acceleration would be expected. Now let's do a problem where a system is in static equilibrium. That means that the net force on the object is 0, and also the net torque is 0 at every point in the object. For example, here we have a plank of mass capital M and length L. It sits on two supports, a 2L over 5 and 3L over 5, as shown in our diagram. The question is, how far to the right of the right support would a mass M vase be such that it just barely tips the plank? We'll use our general method for solving this question. First, we'll think about our assumptions. We assume that the mass is uniformly distributed over the plank. There's no air resistance. We know the mass of our plank, we know the mass of our vase, and the length L. We also know the positions of the two fulcra as shown. What we want is the distance x. We start by drawing an extended free body diagram of the plank. I'm leaving off the normal force of the left fulcrum. That's because just barely tipping means that that normal force would just go to 0. So I have mg, the gravitational force at the center of mass of the plank. I have the normal force on the plank from the support, and I have the normal force on the plank from the vase. I include the pertinent distances on my extended free body diagram. The gravitational force is in the middle of the plank, so it's at 1/2 L. The normal force coming up from the support is at 3/5 L. And x is the distance between that support and the normal force pushing down from the vase. Then I do a simple free body diagram of the vase. I have the normal force on the vase from the plank pointing up, equal and opposite to the gravitational force pushing downward. For the vase, we have that the sum of forces equals 0, equals the normal force minus mg. From the extended free body diagram, I'm going to choose the right-hand side fulcrum as the pivot point, positive clockwise direction rotation. Gives me the sum of torque equals 0, equals the normal force on the plank from the vase, a distance x away from the pivot point, minus the normal force on the plank from the support at 0, because that is the pivot point. And then mg at the distance L over 10 has a minus sign. That minus sign comes in because that gravitational force would rotate the plank in the opposite direction. I can solve my first equation for the normal force equaling mg, and then substitute that in, giving me mgx equals capital Mg times L over 10. I can simply solve for x. X equals the capital M over small m times L over 10. This makes sense. The larger mass would give a larger x value for the position of the vase. The larger the mass of the plank, the farther over to the right the vase would have to be. A larger mass for the vase would give a smaller position, since it could tip it closer to the fulcrum point. To recap, we define torque as the cross product of the position vector and the force vector. The magnitude of torque can be written as Rf sine phi, where phi is the angle between the position vector and the force vector, and we found the direction of torque using the right-hand rule. Then we looked at the Newton's second law equivalent in the rotational form. Net torque is a product of the moment of inertia and angular acceleration. We drew extended free body diagrams to include the torques. We chose a pivot point. We also chose a positive rotation direction. Then we wrote our equations from extended free body diagrams. For systems in static equilibrium, where the net force equals 0 and the net torque equals 0 at every point. Thank you very much for coming. Please come back again soon.